Welcome to the fourth class meeting of the Introduction to Digital Signal Processing. As usual, the homework will be assigned and will be due on Tuesday. This time there will be the theory problems, not just the MATLAB problems. So you'd better review the discrete time signal and system part covered in the previous class meetings. So we are still working on chapter 2, and I'm going to finish the first handout marked as the 2, I remember from the homepage. But anyway, so here goes the review. We review the idea of discrete time signal and discrete time system. The keywords is that we are going to rewrite or represent a given discrete time signal as a linear combination of basic fundamental signals. This is the entire theme of the signal processing, not just the discrete time signal processing. Even in continuous time signal processing, we need this. Got it? So this is very important. For example, given a digitally modulated signal, sometimes you can artificially decompose the signal as a sum of digitally modulated signals. For example, in orthogonal frequency division multiplexing, that is abbreviated by OFDM. This is the waveform adopted in most of the current Wi-Fi systems, and also most of our current cellular mobile standards. And this OFDM signal that is applied or that is extracted from our antenna can be well approximated by a real valued bandpass signal, but it can also be decomposed as summation of multiple subcarrier signals. And each subcarrier conveys a stream of data symbols. So this idea of rewriting a single signal as a summation of multiple signals is very, very important. Okay, so please remember this. Anyway, I will repeat it today by talking about convolution sum. Anyway, as basic signals in this discrete time signal processing, we have unit sample or unit sample function or unit sample signal, or sometimes discrete time delta function, unit step, real exponential, real sinusoidal, complex exponential, complex sinusoidal signals, etc. One of the most important class of discrete time signals, so here is the set of all discrete time signals. Of course, the subset is very small, but let me exaggerate the size. So here is the subset of periodic signals. And among periodic signals, we have some complex sinusoidal signals. The reason why this subset is not contained in periodic signal is that e to the j omega n with omega not the integer multiple, rational multiple of 2 pi is not periodic. Okay, so remember this one. This is very different from the similar situation for continuous time signal set. The set of all continuous time signals has a subset periodic signals, and here we have complex sinusoidal signals. Got it? And these are all in the form of e to the j omega t. Got it? So whatever omega we have, a continuous complex sinusoidal signal is periodic. But actually many discrete time complex sinusoidal signals are not periodic. Got it? Anyway, and I also talked about the uniqueness and existence needs to be considered after you define something. This applies not only to discrete time signal processing course, but also whenever you do something very precise. Try to define something. Try to have a consensus with the terminology, even when you have a debate with your spouse after you get married. Okay? So it's like if you find some video clips about so-called spouse battle or bubu sound, then most of the consultants says that the problem of the couple is that they never agreed about the terminologies they argue with. Right? So defining something is very important. And then sometimes try to find whether what you have just defined is does exist or not. Okay? And also when that thing exists, try to find whether that is unique or not. Sometimes this simple procedure, try to define something, check the existence, and check the uniqueness. This procedure, this automatic procedure, makes your thought very, very clear. Got it? Anyway, and then we started to talk about discrete time systems, and the definition is very simple. A mapping rule. There is a mapping rule, which means that something goes in and some other thing goes out. That is mapping rule. And this mapping rule admits a discrete time signal, and this mapping rule generates another discrete time signal. In that case, this mapping rule is called a discrete time system. Got it? And simple moving average, in Korean, 단순 이동 평균. Sometimes this simple is just dropped, and also everything's dropped, so 이평, okay, is very popular in stock trading. So you've done something, some simple programming about the Kospi data for homework 2 and 3, and probably this new homework will ask you to draw this simple moving averages. Got it? Anyway, so the simple moving average has the input-output relation very simply given. It adds up M1 plus M2 plus 1 terms of the input. And this input time argument runs from, for example, is it M2 or M1? Just a second. Okay, M1. N minus K, A negative M1, M2. Okay. So past M1 terms and future M2 terms and current term with index K equals 0 are arithmetically averaged. However, in reality, especially in stock market trading, you can never observe future values. So they limit their lower limit to 1. One of the reasons why they do not set it 0 is that probably they are using that value, moving average, for today's trading. And today's price is not yet determined. Got it? Anyway, so you will implement that one and draw some lines. There was some emphasis on the convention. So for example, I say that this is a DT signal, and input is X of n, and output is Y of n. it does not mean the output at time n is only determined by input at time n. Actually, this mapping rule admits entire input signal and generates entire output signal, mathematically speaking. Got it? So some people love to write this way, but it's so cumbersome, so they just drop. But don't be confused. I never got confused, actually, but when I was teaching in some past year, I found that some student had serious misunderstanding. Okay, of course, there is some system whose output is not dependent on other input values. For example, suppose you have some constant times the current input squared. Then, in that case, your output at time n is not dependent upon any input at other than time n. However, even though we do not write this parentheses and subscripts and superscript, what we mean is that, as you see here in simple moving average, at the ultimate case, we may use entire input signal to generate the output. Okay? Anyway, so memory system is a very strange thing, but it's not the only one. By the way, we've learned a lot of mapping rules throughout our education. When we were middle schoolers or elementary schoolers, we really studied kind of memory list system. For example, in our middle school math, we usually thought about something like this, especially polynomials, something like this. Even though there is no time parameter, we may think about a discrete time system whose input-output relation is given this way. Let me ask you a question. Is this discrete time system is the discrete time system with this input-output relation, is it memoryless? And your answer is yes. So in some way, what we learned so far before we take the signal gen systems, the mapping rules we learned were for memoryless systems. Got it? Cosine, sine, and something. Anyway. Today, we more focus on discrete time systems. First, we will study what is a linear system, and then what is a time-invariant system. The combination of these two, linear time-invariant system, is very important. I will just state the properties, and we will think more about it in the later sections. And hopefully, we could easily cover up to this bibo stability, bounded input, bounded output stability over discrete time system. So here are the properties of linear systems. What is the definition of a linear system? Of course, discrete time linear system. So here is the definition. A DT system is linear. Of course, we don't need this one if we say that this is the statement related to a definition. If this holds and that holds. Sometimes this is just simply combined as what? T A1 x1 of n plus A2 x2 of n equals A1 t of x1 plus A2 t of x2. Here again, the argument of this mapping rule named T, capital T. Here capital means capital letter T. Okay. Some people, if you take some courses in YouTube or if you go abroad, study abroad, then professors will say the cap T. Okay, that means capitalized t. Okay. Anyway, you must understand this square bracket can be just replaced by parentheses or curly bracket, anything. What is important is that the argument is not the input at the time n. It means this signal, discrete time, entire signal is the input to the mapping rule. But as I told you, we don't want to have this complicated notation to make everything precise. So we just drop that parenthesis and runs from negative infinity to positive infinity, something like that. Okay. Anyway, so what does this mean? Your input to the system is a linear combination of two discrete time signals. Here, linear combination means weighted sum. Here, weight is A1. Here, weight is A2. Got it? And then linearity, by definition, means that when this is the input to the mapping rule, the output, this is the input to the mapping rule T. The output is what? This input signal's output weighted by A1, and that signal's output weighted by A2. So this is very similar to what you have seen in linear algebra. Okay? If you have matrix A, and if you have a scalar A1 and vector x1, and scalar A2 with vector x2, after you expand, what do you have? A1, x, AX1 plus A2, AX2, right? So actually, the mapping rule, whose input-output relation given by a matrix vector multiplication, is actually a linear system. So that's why we call the course as linear algebra. Got it? So this is a special case of a linear system. This is also a special case of a linear system. And as we've seen in signal-gen systems, a continuous time signal whose input is a continuous time signal, whose output is a continuous time signal, can also be defined as linear if what? The mapping of a weighted sum of two continuous time signals is what? The weighted sum of two continuous time signals outputs. Got it? Anyway, so this is the definition of linearity. So you understand what does this mean? This is called y1. This is called y2. So if you apply x1, you have y1. If you apply x2, you have y2. Then if you apply a1x1, a plus a2x2, then you have a1 y1 plus a2 y2. Here, instead of a1, a2, the textbook used the a and b. Here goes the examples. Ideal delay system is linear. Why? Why? You may use definition. Okay. So you do it yourself. Moving average is also linear. It's not that difficult. The problem is that this is not linear. You can easily show. And what about so-called accumulator? Here, be careful about the upper limit and lower limit and the argument of this summand. Okay? What does this mean? The output at time n is what? The summation of the input from time indices n through past infinity, right? So current output is the summation of all the inputs up to right now. And the question is this a linear system? And you can also show it is true by using the definition. And you do it yourself. It's not that difficult. Now here comes the second important definition. Of course, a DT system is time invariant if blah, blah, blah. So this is the precise statement to define a discrete time system. And what is the time invariance? Of course, time invariance can be defined in many different ways, which are mathematically the same, but we want to have a very simple motivation. What is that? You've learned in, for example, math for electrical engineers A, 전자수학 A, on probability and random processes. You learned about stationary random processes. What was the definition, by the way? Stationary random process has the statistical property invariant under time translation or under your choice of time origin t equals 0. Almost the same idea applies to define time invariance of a system. So time invariance means that your choice of time origin doesn't change the property of the system. So simply, it says, suppose here is your mapping rule named T, and here goes the input X, and you have the output. Then this is time invariant system, means so you choose different time origin. So by subtracting n0, n0 could be any integer, you just choose different origin. Then what? You have y that is also has the same time shift. Got it? So this is the definition. And this property must hold for all pair xn, yn. Okay? We have this property. For all n0, an integer. Got it? So this property must hold for every possible input-output pair. Of course, here I do not say that every possible x can be combined with every possible x. The y is the output of x. So you have the pairs of signals, and each pair, the input is translated, then output is also translated by the same amount. Then the system is called time invariant. So here goes the example. The accumulator we've seen here is not only linear, but also time invariant. And you can use the definition to show this. Okay. Okay, let me just skip. And here goes the stability. And stability is kind of very strange terminology. And this is the story in engineering. We want to define some new idea. And we have some new idea to graduate, for example, to get the master's degree and to get the PhD degree and something like that. The problem is that we want to name the new concept using some new terminology. But you cannot just name your new definition something totally non-existent. By the way, there are many products, the commercial products that has very misleading names. For example, Evian, that is very famous. Some pure water, something like that. They say that this name is from the word naive, okay? And they just transpose the order of the word. And sometimes people use, for example, full self-driving, but usually they have some small footnote and saying that this is not real full self-driving. So what people do is that they take the words that already exist and they use they do not use the terminologies in what was meant. And that gives us a lot of confusion. And it is not just for commercial products, but also for almost every academic concepts. So here, we use the word, ordinary, daily use word stable. And we have used that word in, for example, stable coin. Probably you know what does that mean. And for example, our political situation is not stable, something like that. So stable, the word already has some meanings. But as an academic or academic researcher, you just have a new idea, but you cannot find any other plausible word than stable. Then what do? You define it. And you say that, okay, here goes the definition. A DT system is stable if blah, blah, blah. And whenever you do, of course, whenever you do, even though this word already has many, many meanings, just forget about that. The definition is solely determined by the following statement. But you don't want to arbitrarily choose when you invent this new definition. So you just do not say that a DT system is stable if it blah, blah, blah. Then you change DT system is white. You don't do that, okay? So whenever you name a new concept, you borrow the existing word that matches as good as possible. But never to be fooled too much, fooled by what you already know. Got it? So you define. But suddenly you find your contemporary other researcher also have the definition of stability over DT system. So for example, Pak Abdul has published a paper on stable DT system. But in the US, for example, Paul Smith has definition that a DT system is stable, blah, blah. In that case, of course, I'm assuming that their definitions are different. Then people will say that this is Kaptol's criteria. So Kaptol defines stable system in this way. Paul Smith defines stable system in other way. So here, the important terminology you have to remember is that different criteria. Okay, criteria. Okay, that is the plural version of criterion. So Pak Abdul's criterion says that DT system is stable if this condition is met. Paul Smith's criterion defines stability as something else. Got it? So there could be many, many, many different criteria under the same name. So be careful. Anyway, here in the introduction to DSP, we use so-called bounded input, bounded output stability. Sometimes simply just drop. The system is stable. And what does that mean? As this quantifier implies, bounded input signal always generates bounded output signal. If this condition is met, then we call the system a bibo stable, bounded input, bounded output stable system. And the problem is that what is the definition of bounded input? Bounded input means that you can find some fixed positive number. Then for every time indices, for every time index, your input signal whose absolute value, or if it is complex, it's modulus or just absolute value, is less than or equal to that number. You must be able to find some finite number. In that case, it is bounded. So let's see. Suppose x of n equals n squared, or n. Is it bounded? No. You cannot find any fixed number that kind of bounds, or that serves as a upper and lower bound of the signal. What about x of n equals cosine n? Then you always know that as far as n is real, this is bounded by negative and positive 1. So any number greater than or equal to 1 can serve as the b sub x. So it's bounded. Got it? So if a discrete time system satisfies bounded input generating bounded output for every admissible input x, then it's called bivostable. Of course, in more detail, we are going to combine this linearity, time invariance, and bivostability at the same time. And an interesting idea allows us to combine these ideas. So after we find some summarizing function, time function, for discrete time system, we will talk about, hey, this means it's linear. This means it's time invariant. This means that system is bivostable, something like that. So here goes simple stable systems, squaring system, and also accumulator. Now, we combine three notions. So suppose this is the set of all DT systems. We have a very small subset, linear, very small system, time invariant, the very small system, causal, and blah, blah, blah. But let me exaggerate. So here, linear. Okay. And we will see time invariant. Of course, we sometimes we want to define, we want to draw here causality, causal systems subset, and stable system subsystem. But these two subsets are very important, okay? Because most of our theory is the systems in this intersection of two ideas, which means we will mostly focus on linear time invariant systems. So here goes the property. So the theorem says a DT LTI system is fully characterized by its unit sample response. You've seen something very similar in signal gen systems when you were thinking about linear time invariant systems. And when I was teaching the signal systems, also I said that that idea can be applied to DT LTI systems. So it's like, given a DT LTI system whose input is labeled as xn, whose output is labeled as yn, what does this theorem say? This input-output relation, okay, the mapping rule, we don't know what it is. It could be accumulator, it could be moving average, right? We don't know, but in order to fully describe what this mapping rule does, you just need to do what? Here, you apply unit sample function and observe its output. Let's say h of n is the response to the unit sample of this DT LTI system. And then, amazingly, this discrete time system fully characterized, which means that completely describes the input-output relation of this DT system, DT LTI system. It's very, very amazing. Okay? So this enables a new idea. So we want to make a DT system that does some mapping rule. And we don't know how to implement that one by using digital circuits. And actually, there are usually more than one way to implement it. So the implementation method is not unique. But so student A may build the DT LTI system using some several components, and student B may build the same system whose mapping rule is same using totally different components. But what's the common? They have the same impulse response. This is called impulse response or unit sample response. And this is very amazing. And let's see why this is true. And of course, many of you already know that if the system, DT system is DT LTI, the input-output relation can be written as the convolution sum of the input and this unit sample response. Okay. So output is completely determined by the input and unit sample response. And we are going to derive this one. And some of you who took signal gen systems before you do military service, probably some of your neurons have deteriorated and forgot how to prove this. And what is the basic idea? Actually, this happened almost same to me. I did very well in signal gen systems, but after a few years, I forgot how to do that. And when I was a graduate student, I read the signal gen systems book again and found what? This is the key. So you rewrite the input signal using what? Weighted, delayed delta functions. So this is the first step. Ready? So as I told you, this is very, very, very important idea. Given a signal, you somehow decompose. Here, decompose means that weighted sum, a sum of these, each signal becomes the original signal. Okay? And especially, each term may be a weighted sum of some fundamental signals, like this. Okay, see that? This is a function of n, and this is function of n, where the unit sample is located at time k, and its height is x of k. And we sum, right? If you have no idea about this one, read the textbook carefully, okay? Textbook explains that one very, very in detail. Okay? Now, what we do is that we consider the output y, that is the linear time invariant mapping. So here the book and the Professor Choi Jun-il use T, but let me just use L, assuming that this, no. Let me just use T, okay. T, this is the mapping rule, and X of n. And now, what do? We just plug in the representation of the input here. By the way, you do it yourself by using your hand, okay? Not just watch folding your arms. Don't do that. According to my experience, the number of pages, the amount of lead in your pencil, sharp pencil, and your eraser is proportional to your understanding of this material. Anyway, so we have x of k, delta of n minus k. Okay, so far it's okay, as far as you know how to approach. Got it? So this kind of represent the signal is the key. Rewrite this signal in this form. Of course, here The reason why we have rewritten the input as a linear combination is because we are going to use the property of this mapping rule. We assume this T is linear and also time invariant. But let's use the linearity first. Now, even though our linearity assumed two signals, weighted, summed, and applied to the system, it could be applied to any countable weighted sum. If you can do two signals, you can do three by grouping 2 and 1. Got it? The problem is that actually we never proved whether this is allowed. This is the kind of hand-waving part of undergraduate signal gen systems and DSP. Precisely mathematically, it's not easy whether our definition of linearity in terms of two signals can be applied to countably infinite signals. But let's forget about that much rigor, because as I told you, as an engineer, we have to interpret positive infinity and negative infinity to just say that what? Very old path, very far future. But anyway, our system handles some finite time. This is just for convenience, okay? So when I was a graduate student, sometimes I had to prove something that is too much as an engineer. But sometimes you need it, okay? For example, if you want to submit your paper to transactions on information theory, then sometimes the reviewers say that, hey, you never proved whether this definition can be applied to countably infinite sum of something, blah, blah, blah. Then I have to prove that part in order to get published. So when I was a graduate student, some best universities, best graduate schools in the United States, especially the professors in systems like control, communications, and signal processing, they ask their research assistants to take math courses like analysis, 해석학, measure theory, 측도론, and measure theoretic probability theory, 측도론적 확률론, to well equipped with little bit rigorous math. Of course, it's far less rigorous compared to the math department students' thesis. But anyway, so I myself also had to take mathematical analysis and measure theory and measure theoretic probability courses. And they all talk about what? Sequences. Sequences of numbers, sequences of functions, sequences of random variables in order to rigorously prove. But anyway, here, let's just assume that they are finite numbers, but very large and very small. In that case, we can just say that, okay, no problem to what? Apply our definition with just two terms. Just think about this one. Suppose you have a linear system and you copy, then in this way, you know that as far as the same identical system is linear, then it applies to what? Any finite weighted sum, right? Anyway, so here we just rewrite this one as what? Sigma k from negative infinity to positive infinity. First, t of xk, delta of n minus k. And now you are okay, right? Even though it involves two infinities. But as I told you, finite, very large, very small. So linearity means that you can rewrite this one. Second, can you take this coefficient out of this mapping rule? Yes, due to the linearity. See that? Be careful. This mapping rule says what? This is a function of time n. Okay? So this is what? A coefficient, constant. So you take that out. Now, what is this factor, capital T of delta of n minus k? What is delta of n minus k? As a function of n, at n equals k, its value is 1. At all the other time instants, the values are zeros, right? Now, this is the input to the system, named t. So it goes in 0, 0, 0, 0, 1, 0, 0, 0. And you have some output. Let's call this one as what? H sub k of n. Here, the subscript is used to clarify that this is the impulse response of the response of the system to the impulse applied at time k. Got it? So you have what? H sub k of n. So far, we use the linearity. Got it? See that? Here, this is just representation. Here, we use the linearity. And from here to here, we just named this signal as H sub k. Now, let's apply time invariance. According to time invariance, what are the relations of these impulse responses? So the response of the system to the impulse applied at time 0, you have some signal. The response of the system to the impulse applied at n equals 1, you have some response. What is the name? H sub 1 over n, right? Now, impulse is applied at, so this impulse is located at 2, then you have the output, and what is the name? H sub 2 of n. What are the relations between these H sub k of n's? So let's think about the impulse response where this unit sample is located at 0. This is the signal. Now, what is the relation between this and that one? So let's rewrite H sub 1 of n by using H sub 0 of n. So at time 0, you have signal. At time 1, you have what? So input is actually delayed, right? So for this one, you apply delta of n. For this one, you apply delta of n minus 1. So the H sub 1 of n must be this one for all n. Then we can easily generalize this way. Am I right? So whenever you got confused, just start from 1, then 2, and many. If you can do 1 to many, then 1 to 3. Sometimes you can immediately know 1 and then many. Got it? Then we may write this one as h x sub k, h sub 0, n minus k. So we can rewrite the output y as the weighted delayed version of the system response to delta of n. And in many cases, we just drop this one and say, hey, we have x of k, h of n minus k. And interestingly, by the change of variable, you can rewrite this one as that one. So the role of x and role of h can be interchanged. It's not that difficult. You do it yourself. Okay. This simple rewriting of this relation gives us very interesting idea. What? The output y can be viewed as a delayed version of impulse responses, delayed weighted version of impulse responses, or our output can be viewed as delayed weighted version of the input signal. Okay? So you have to be well knowledgeable about these two different ideas. Sometimes this is better to understand what's going on. Sometimes this is better to understand what is going on. So you have to keep this in your mind. By the way, this summation is mathematically named as what? The convolution sum. Of course, mathematicians will say sequences, but it is signals x and h is denoted by xn asterisk hn. Be careful. I say discrete time signals. So again, precisely speaking, you need these to make everything precise, right? Be careful. This operation is not on x at time n and h at time n. This operation involves the entire signal xn and entire signal h. Got it? And defined as what? As this. And some textbook loves that one, some text loves the previous one, but anyway, you can easily see that convolution sum or convolution summation is a commutative operator. 교환 법칙이 성립하는 연산. Got it? So here you have almost the same idea, but be careful again. So here goes something interesting. So suppose you have y of n defined as the convolution sum of two signals. Then let me ask you, what is this one in terms of y? So you define y as the convolution sum of these two signals. Now, you just delay one of the signals. Then what would be the output in terms of y? And mathematically speaking, you have to show this result, but we already know that convolution sum describes the input-output relation between, the input-output relation of a discrete time system. And the system has linearity and time invariance. Now, your output, new output, right? Let me do this first. It's confusing. So let's delay the input first, even though it doesn't make too much difference. But suppose the input is delayed, then what would be the output? Delayed version of the original output. And convolution sum allows the same role for the input and impulse response. So if you delay the impulse response, your output is also delayed. Got it? Now, what happens if you delay the input and delay the impulse response at the same time? Then your output is delayed by 2 and 0. Got it? That's what it says. Okay, so if you delay input, and then you have that one, not y of n minus. Okay. And here is how you compute this convolution sum or discrete time convolution. So the textbook visualizes how you interpret this sum or that sum. And let's see. So let's assume that this is the input signal and this is the impulse response. And here, let's use, which one? That's too small. Okay. Oh. Okay. So as you see that, here are the impulse responses delayed. So we used this definition. Okay. So let's decompose X as what? The unit sample shifted by 2 to the left and multiplied by this height. And what is the response to this impulse, ignoring the others? The output would be the impulse response left shifted by 2 and scaled by this amount. So here you have, okay? This is left shifted by 2 and scaled. Now, what is the response of this impulse? That one just scaled. So here is your component. And what about that one? This impulse response delayed by 3 and flipped and scaled. So you have that one. And in order to have the entire output, you just sum. And this is the output. Similarly, if you sum these 3, you have the input. Got it? So this figure 2.8 in our textbook shows how to compute the convolution sum by using the delayed weighted impulse responses. But you can do the other way. That's not that difficult. And I believe, yeah, this is using the same idea. You do it yourself. It's not that difficult. Okay. And here goes the properties of LTI systems, more in detail. So the first thing is that the convolution sum as a mathematical operator. So convolution sum is something like this. My colleagues, generation did a lot of this stuff when we entered elementary school. Like, hey, this strange thing marked plus, and what is the output? 2 inputs, right? Input 1 and input 2, and the kids say 3, and teacher say that good job, something like that. Now we do something similar. This is no longer plus. This is the convolution operator. And here you have X. And here, you have H. Then you have X H defined as xk, h, and minus k. Got it? And we already know that this output does not change even if we put h here and x here. And this property is very similar to our ordinary arithmetic operator addition, right? 1 plus 2 equals 2 plus 1, same thing. And also, it's the commutativity holds for multiplication, as you know. And here was something similar. So convolution sum, that mapping rule with two inputs and one output, is commutative. 교환 법칙이 성립하는. Okay? So you see, the order doesn't matter. And second is distributive. What does that mean? And this left-hand side must be interpreted as what? Then let's say output is y. And here on this is left-hand side. What is right-hand side using this figure? So here you have xn, h1n, and here you have x, h2, and y. Got it? So this use of single convolution sum can be implemented by using two convolution sums. And this kind of rewriting of one function or one operation into an operation with sub-operations is very important. Even though mathematically they are the same, but when you implement using electronic circuits, some of your technologies is better suited to this one. You sum them first and then use convolution sum. Is better, but some other technology may have better performance when you convolve the signal in two different convolution sum function and just add. Mathematically, same operation can perform differently in the real world. So you'd better have many different representations of same operation, because sometimes this works better than that one or vice versa. Whenever you have some non-ideality, means you have some practical system that has production errors, that has some noises in the system, that has some cosmic ray hitting the circuit. So be careful. What about this one? This one has different left-hand side and right-hand side. So this one is more interesting. So let's see that first. So you have two inputs, x and h1. Then this and h2 is convolved. What does that mean? Something like this. So you have what? Kind of serially connected two convolution sums. Let's say this is y. And what does the right-hand side mean? Amazingly, they generate the same output, right? So this is associativity. And By combining commutativity and associativity, you have something interesting like this. So let's think about this right-hand side. First, you change the order using commutativity. And then you group these two. See that? This is associativity. You group these two or group these two. Okay? So compare this one and that one. H of n convolve with, X of n convolve with H1 and H2 convolved is same as X convolve with H2 and H1 convolved. So you can change the order of the convolution, but you have the same result. Right? This is very interesting. So it's like this one. Suppose you have input X. Then you have a discrete time system with impulse response H1. Its output is applied to H2. Mathematically speaking, what is that? It's like Xn convolve with H1 convolve with H2. And what is this one? Xn convolve with H2 convolve with H1. And by using the associativity, you have what? So actually, what does this mean? This means that when you have a serially interconnected discrete time LTI systems, be careful. This is for two LTI systems. If either one of the systems is not LTI, you can't do this. You cannot switch the order to have the same result. But as far as they are two LTI systems, it's okay. The problem is that in the real world, we build some system that is very LTI in some range of input. So suppose you have built some circuit, electronic circuit, that behaves similar to this system. So actually your system is not LTI, but in some range of the input, that is very good approximation to the first system. And you also have the second system that is not LTI, but it behaves very close to LTI with impulse response H2 in some range of input. In that case, your serial interconnection of H1 and H2 may be okay. But if you change, suddenly the system fails. So be careful. Okay? Theoretically, this is true. But in reality, you just swap the order and suddenly system does not work. So be careful. Okay? Always remember, we are engineers and our math is for our convenience. To model the system so that we can handle mathematically, and we want to know what kind of extreme cases or what kind of non-intuitive, 비직관적인 result can be obtained from some rigorous math. We want to know that. The problem is that sometimes our system, real-world system, cannot be well modeled by our mathematical model. So always be careful and remember, we use mathematical models to understand the real-world system. If you forget this one, sometimes you have some problem, just you cannot understand. It should work, but it does not, okay? And usually that happens when you have a modeling problem. Anyway, by the way, what about this one? This is what? You have two parallel systems whose outputs are added. And these two parallel two parallel subsystems can be just combined into a single system. What does that mean? by mass, this one. See that you have a single system. You have two systems with the same input. So this is simply distributivity of DT-LTI systems. So sorry, distributivity of convolution sum, which in digital signal processing can be interpreted that way. And again, sometimes this makes your system more robust to some error. Sometimes this is better. Got it? Which one is better depends on your technology to implement your system. For example, suppose you use just some embedded system. So very powerful software is just working, computing everything. In that case, either one will be okay. But you really use shift registers and some potentiometer to implement that one, then depending on the production precision, this may give you far better product than that one, or vice versa. Right? Same thing here. We know that serially interconnected system, its order can be changed, but sometimes these two impulse responses may be combined into one. And you may say that, hey, we'd better have just single system than two systems. But sometimes modularize each one may reduce the cost. For example, this system, in order to have that system, you have to use some foundry to have a new digital system. So your chip goes to TSMC or Samsung and it costs $20 million. But you find that, hey, this is very cheap and available. That is also very cheap and available. Then just purchase them and connect. That kind of idea you have to have. Right? By the way, let me ask you some questions related to LTI. So we know that an LTI system is fully characterized its unit sample response or impulse response. So many cases we just write this way. So this is the popular description. By the way, in signal gen systems and DSP, we love this block diagram. But in computer scientists and engineers love graph. So sometimes they just have two dots and one line and say that this is X and that is Y. And where is H? Somewhere here. So be careful. Ready? I really had a lot of trouble to get acquainted with the graph-based representation of signal gen systems. But anyway, so keep this in mind. So this is theorem. And here goes the first question. What if LTI system is causal? By the way, causality is also very important thing. Simply put, causality means that 인과율이 성립하는 system. What does that mean? This is very confusing definition. But this is the only one. So suppose X1.
It's time to wrap up, Dr. Joe.
Okay. Let me define the causality next time. And here goes the question. So what if LTI system is causal, then can we say something in terms of the impulse response? Also, about bibo stability. Suppose an LTI system is bibo stable, then can we say something in terms of the impulse response? Got it? That is the idea. Okay, that's all for today.